Hey students, I thought it might be useful to a few of you if I looked at chapter 17 and did some examples. I ran out of time in class and it's kind of nice to see some of these, although you have a lot of homework problems to do and I've done a lot of videos of the homework solutions, so maybe that's enough, but just in case this might be helpful to a few people, I decided to look at my example list, and had we had more time in class, I would have lectured on these examples from the back of the book, these 6. So let's start here with number 4. And number 4, I've printed it up here. It says this: the speed of sound in air, measured in meters per second, depends upon the temperature according to this equation. Now, you might remember that in class, we derived this, or at least I should say we nearly derived it. The other textbook actually derived it, the OpenStax, and came up with this 331 over the square root of the temperature on the Kelvin scale over 273. And then through a little binomial expansion, or even a Taylor series, however you want to do it, you can show that that comes out to approximately, and here's the binary expansion, 331, and then it's 1 plus temperature on the Celsius over 273 raised to the 1/2 power. And if you expand that out, you do get, with a little more accuracy, what they're saying here, 331.5 plus 0.607 and temperature on the Celsius scale. So that's where that comes from, and like I said, that's worked out there in the textbook. Well, I'll save some time. I was going to show you the textbook, but let's just take that. Then it goes on to say, in dry air, the temperature decreases by about 1 degree Celsius for about every 150 meters rise in altitude. A. Assuming this change is constant all the way up to 9,000 meters, what time interval is required for the sound from an airplane flying at 9,000 meters to reach the ground on a day when the ground temperature is 30 degrees Celsius? So in this picture, if you will, we'll have a airplane flying along, and the ground is way down here somewhere. And it produces this sound, and up here it is cold, and down here it is hot. And you can see in this equation that the speed depends on the temperature. And so the speed up here would correspond to slow, or at least slower. And then it would go faster and faster and faster. And so each, you might say, microscopic distance of, say, dx, covered in a microscopic amount of time, dt, would be different than up here, where you would have a little bit of distance, dx, and over a little bit of time, dt. Of course, going back to Physics 121, we know this. We know that velocity is then dx dt. And so what we could do is, separate these out. Let's see, I think we're looking for time. Let's come back here. What time interval? So if I were to solve this equation for time, it would be this, that you would have some small moment in time equal then to this dx, so a small distance over the velocity at that particular position. And of course, the smaller you make that, that's why we use our calculus, the more accurate this is. So in a microscopic limit, this is a constant value for a microscopic amount of distance, and then we get some microscopic amount of time, and then we would add them all up. That is, we would do an integration, and then that would give us then the total time t. And so this is what we need to accomplish. This is the heart of this problem as we put together, two concepts we learned. One is that the speed changes with temperature, and the earlier one in the earlier class is how time and position and velocity all fit together. And I suppose a third piece has to be put in there because we've learned that velocity depends upon temperature. And then they're helping us with a little phrase here, giving us how temperature depends upon on distance. And that's going to really help us here because we're integrating over this distance. We're going from, 0 to 9,000 meters. Or actually, we're going down. We're going from the top 9,000 meters on down. In other words, what we know is how velocity depends upon time. I'm on temperature. But what they're telling us is how temperature depends upon x, the height, the altitude. And so we can write this really as a composite function, but then say we know how the velocity changes with position. So again, that's going to be kind of the key to this problem. So if I kind of make a grid here, and say, okay, here's going to be the ground, and here's going to be the airplane, and the sound's going to come down here. I guess, like all problems, I need to pick, where do you want to call 0? And I think it's most natural to call the ground 0 and the plane at 9,000. And so that means you're calling up positive. And I'll stick to that. I guess I don't mind that. I guess I just want to be careful to realize then that the velocity then of the sound waves are a negative direction. Because when I, did this little calculation here, I guess let's see, depending on how you want to look at this, I was at least implying, and I guess this is true, but part of that was, magnitude, and that's what I guess this is. This is the magnitude of the velocity. So I wouldn't want to just plug this in. I would want the negative of that because this velocity is going to go down. That's probably the most obvious thing that I need to be careful with, and the thing that I could really mess up mathematically here if I don't take that special moment and say, okay, I need to read the math. What is the math really telling me here? What is my coordinate system? And as I keep telling you guys, that, physics is about knowing how to apply a few but powerful fundamental concepts to explain a universal phenomenon. And, and we don't do a whole lot of memorization, but a lot of deductive reasoning here. And so we've got to just be careful and consistent. And so if we're going to call this 0 and this 9,000 and have the sound go from the plane down to the ground, and nothing's wrong with that. I think that's the most natural way to do it. We just want to be careful not to use this equation directly because it gives us a positive value for the velocity, and we need a negative one. And so we just got to put a negative in front of it. It's not a big deal, but it's something that I could see could be easily carelessly overlooked. Probably the harder thing, though, is really this calculus, really saying, okay, what I'm going to do is use my calculus. I'm not going to treat this as kind of a algebraic high school type problem. I'm going to integrate. I'm going to add up. I'm going to do my calculus here. Okay, so with this in mind, I'm going to come back here and say, okay, so I'm trying to get the total time. And I get the total time by adding up little small moments in time. And what's equivalent to a small moment in time is a small distance, e divided by its velocity. And my small distances would be measured from starting up at the high altitude of 9,000 meters and going to 0. All right. This, though, probably needs some more work. As we said, we know that the velocity, and maybe I should put the magnitude of the velocity, is given by that equation at the beginning, 331.5 plus 0.607 temperature on the Celsius scale. But then we should, from the words they give us, be able to get how temperature changes with position. And that's where we're going to probably need to give some thought. In fact, this looks like this might turn into a pretty long problem. So let me refer to that as page 1, and this one up here is page 2. The phrase they said is it changes 100 or 1 degree for every 150 meters in rise. So it's a constant change. That is, if you were to plot temperature and x, the height up. Maybe I should switch that to a y, but I've been working with an x. So let me refer to this as the x-axis going up. Okay. Then I guess I'm going to have some temperature that will be on the hot side. And I might as well do this on the Celsius scale. So we'll say that this is a plus 30 degrees when we're at the ground level. And it's going to be decreasing as x gets higher and higher and higher. So it's 30 degrees down here on the ground, and if we go higher, it goes down, down, down at a constant rate. So that's why I would draw a straight line. And I'm not sure how far to draw this line. I'm not sure if it's going to go all the way to 0 degrees by the time I get up to 9,000 meters, or maybe even go negative. I suppose I'll find out here in a second. But I do know this. The equation for a line would be, of course, y equals mx plus b. And in this case, the y-axis is the temperature on the Celsius scale. The x-axis is x. The y-intercept is my 30 degrees Celsius. And the m is the slope. How does it change on the vertical axis compared to the horizontal axis? And they say it goes, down 1 degree for every 150 meters. So this is a negative 1 over 150. And so that would be my equation, if you will. Maybe I'll simplify it here, but the temperature would be a negative x over 150 plus 30. Not a big fan necessarily of the 150, and the reciprocal I'm not a big fan of either. Maybe I'll just kind of leave it that way. But I am kind of curious then about the height of 9,000 meters and what the temperature comes out to be. So negative 9,000 divided by 150. Let's go enter that. So that's a decrease of negative 60. So this is going to go all the way down, decreasing negative 60. So this should be somewhere at negative 30. And you can see when I finish the equation and add 30 to it, I'm going to finish it at negative 30. So in my picture, I'm going to just say, okay, negative 30 here. So it, I guess, starts here cold at a slow speed, goes faster and faster and faster, and some places it gets to 0 degrees, and then faster, faster, faster. I guess it's linear, so it's halfway. But eventually, gets to the ground level, 30 degrees, maybe a desert, I don't know. 30 is pretty warm, but not necessarily a desert. Anyways, there is my equation then, right here, of temperature based on position. And of course, this is my velocity based upon the temperature. So let's put this composite function together. Again, I guess I'd call this velocity as a function of temperature and temperature a function of position. So it'd be the 331.5 plus 0.607 times then the temperature equation, which is minus x over 150 plus 30. And so this is 331.5 plus, and I guess this right here would be the 0.607 divided by 150. So let's call that a 0.00, let's call it 405x, oh, negative. And this is the 0.607 times 30. And so this would be 18.21. Okay. And if I put these two together, I'll write this one first, negative 0.00405x. And then I'll take this and add it to the 331.5 and get a plus 349.7. This then becomes the velocity as a function of position. All right, now that I did all this, I'll call it the side math, that is, put together the temperature of position, velocity versus temperature, and then the big one is the fact that we have to integrate then. I can say, okay, the total time then is this integral from a height of 9,000 meters to 0, dx, and then we're going to integrate the velocity. But again, let me just kind of repeat here. My velocity is negative of this equation because this equation is based upon positive numbers. So the negative of that is a plus 0.00405x. Okay, then minus 349.7. And of course, you can probably now see this is a perfect U sub. And so if we let U equal the plus 0.00504x minus 349.7, then du becomes plus 0.00405 dx. And so when we take this equation down for time, we can replace the integration of dx with du. So in place of dx, I'm going to put du over 0.00405. And then I'll put a du. And so this is going to come out to be, let's see, 1 over 0.00405 for that number. And then I have the natural log of u evaluated from the two endpoints. I didn't bother to figure out what the endpoints are in terms of u. I could, but I find it a little more useful. Maybe not this time, but most of the time, instead of changing my values of my endpoints for x into values of u, is just to change my u back to my x's here. So this would be the natural log of plus 0.00405x minus 349.7, then evaluated from 9,000 to 0. Guess I should be a little extra careful with absolute value. Probably best to maybe write it this way, because this would be the log of something minus the log of something. And when we do that, we can write a log minus a log as a log of the quotient. And so if I put in a 0, I get a minus 349.7. And if I put in my 9,000 here, what do I get? 0.00405 times 9,000 minus 349.7. And I get a negative 313.25. And this is kind of what I was saying here. I want to be a little bit careful. Many mathematicians might put absolute value here. But if I write it as the quotient, I'll have two negatives, and so it's positive, because obviously you don't want this ever to be the log of a negative number. And then I get, let's see, I'll just get rid of the negatives by hand. And so I've got 349.7 in the top and 313.25 in the bottom. And I'll take the natural log of that. Then I'll divide that by 0.00405. And that'll be about 27.2 seconds. Nice. That was page 3. So that actually had a lot in it. I hope that wasn't too overwhelming for a beginning one. It took me over 20 minutes to kind of talk it through. I'm not even sure we're done, because this is to reach the ground. Then it's a part B. Compare your answer to the time interval required if the air was uniformly at 30 degrees. And that actually I kind of like, because sometimes we call it a back of an envelope calculation. You might even call it a careless mistake, is to forget that the speed changes with the temperature, and just realize that, oh, wait, it's 30 degrees. Well, yeah, it's 30 degrees down on the ground. And so if you did that, you would be saying, well, the speed of the air, 331.5 plus 0.607 times 30 degrees, would be 349.7 meters per second. And again, if you were careless and forgot that the temperature changed, as you went up, you would just say, okay, well, it's 30 degrees here on the ground, and then, okay, that would be the speed of the sound, and then, of course, then it's going to travel the 9,000 meters, so you might just do a simple calculation where you treat the speed as a constant value, and you get a time. And so if I do that, I get 9,000 divided by 349.7, and you get about 25.7 seconds. And of course, you get a number that is a little off, not because you didn't take into account that it slowed down as it went up to the colder air. And that's why you got a number that was a little off, and notice that the number that's off is a smaller amount of time, because you think it's going to be traveling this fast speed all the way from the airplane to you, and it didn't. When it left the airplane, it was going at some lower speeds. It didn't get to this fast speed till it got to you. So overall, it would be about 2 seconds longer. So good. I'm glad the author asked that at the end. That's a good comparison question, and because it's just a hair longer than the part B. Part A is just a hair more than part B. It does make you feel like you've done part A correctly, especially after all that work. You're like, okay, I could have easily made a mistake in all that work. All right, well, let's go on to our second one. My second example here is number 13. And number 13, where's that paper? Here it is. I printed that one up also. And number 13 says this. It says, write an expression that describes the pressure variation as a function of position and of time of a sinusoidal sound wave in air, assuming a wavelength of 1/10 of a meter and the change of maximum pressure, that's the amplitude of 0.2. Well, you might remember from the lecture or from the book that we said that you could think of sound waves as a pressure wave. You could also think of it as a displacement wave. The kind of tricky thing was that the displacement wave is at a different phase and by 90 degrees compared to the pressure wave. I don't think we'll be needing the displacement wave here in this problem because they said, write an expression that describes the pressure variation as a function of position and time. So I want the delta P. And the maximum variation in pressure is given as 0.2 pascals. And then it's a sine. And then the K value, which is 2 pi over lambda. And lambda here is 0.1. And so that would make 20 pi. And so here is 20 pi times x. The minus or plus is for what direction it's going. The minus is to the right and the plus is to the left. They're not real clear here, so I'm just going to leave it as both a minus and a plus. It just says right, description. And I think maybe by default they mean to the right. So a minus sign, it would be by itself, probably would be fine. But remember, the angular frequency is 2 pi times the linear frequency. Or the 2 pi times the velocity over the wavelength. And I think they want us to imply, because I did say, in air, and kind of the default is room temperature if they don't say what the temperature is. The problem we just did, number 4, we went into great detail of how that velocity changes. So we're going to just say then that it's that famous 345 for the speed over 1/10, which I guess then makes this a 3,450. And so if you double it, let's see, that 450 becomes 900, and that becomes 6,000 pi. So this would be 6,900 pi t. And that's probably good to stop there. Sometimes it's nice to write out in a decimal form what things like 20 pi is. I'll call it 62.8. And also the 6,900 pi. Because a decimal, I think, is a little bit easier to understand. When I see things like, 6,900 pi, I'm not real sure where that is. Is that, is that more than 10,000, less than 10,000? Is it 20,000? Is it 15,000? And so it's kind of helpful to write a decimal. But whether you write a decimal or not, I think we've answered the author's question here. So that's a much shorter and I think easier problem. I guess that's why the first one was coded blue for medium, and then easy, or at least the easiest. There's no easy ones, but easiest. And then I guess likewise here, number 19. And so number 19. And it's, oh good, it's a black one, so maybe this one isn't too bad. Then we got some blue ones. Oh, and the other two are blue ones. Okay. All right, so looking at this black one here. Here it says, the intensity of sound waves at a certain distance, a fixed distance from a speaker vibrating at 1 kilohertz is 0.6 watts per square meter. A, determine the intensity that results if the frequency is then increased to 2.5 hertz while a constant displacement in amplitude is maintained. Well, the heart of this problem is getting at the equation we worked out and the book worked out for the intensity of sound waves. And like the string waves we did in previous chapters, 4 factors come into play. One is the density of the air. Kind of makes sense because part of the sound waves are the movement of those air molecules. So, the heavier they are, the more kinetic energy they have. The rate at which they approach you, and so I'll call that velocity. And that kind of makes sense because power is energy per time. So the energy has to do with the mass, and then the energy per time would be the rate. Now, how quickly they move is its back and forth, is its angular frequency squared. So that's kind of like kinetic energy. So kinetic energy is kind of like 1/2 mv squared. And then this is the time factor, how quickly. So these together would be like kinetic energy, and then how quickly does the kinetic energy kind of move towards you. And so that's kind of the rate of kinetic energy right now. And then, of course, it's also the amplitude squared, because as waves hit you, they're being, they're not really molecules on a spring, but let me use an example. If they stretch them, there's a potential energy as well as a kinetic energy. So this is related to that stretching of the spring. So that's the equation I'm going to use. And so what they're really saying in the first part of this, even though they didn't give me the individual pieces, like the density of air or the speed, or even the well, I guess they did give me the frequency, the amplitude. I guess I could. I don't need to. Maybe that's maybe that's kind of the uniqueness of this problem. The author maybe said, look, if you wanted to, it wouldn't be unreasonable to look up the density of air, because that's a speaker. I don't really know if it really says air. It doesn't really say the temperature, so we don't really know the speed. But if we take this, as air, we know that number, and then at room temperature, we know that number, and then they give us the frequency, they give us the intensity, and we could actually find then how far these molecules move and use that going forward. But I don't think that is really what they want you to do in this problem. Although that would be the longer way. So maybe that's, like I said, the author's intent that, hey, there's a long way to do the problem, and then there's a short way. And especially an exam problem, do the short way. You may get it right the long way, but you might then run out of time for the other part of the problem. So it really is a test of knowledge. Because here's what I'm getting at. Let's just say all these factors, even though I haven't bothered to look them up or calculate them individually, I do know that all these factors come out to be 0.6 watts per square meter. That's what the beginning of the problem says. The intensity of the sound waves at a fixed distance from a speaker vibrating at this rate is this intensity. Okay, so then, if I come along and I look for the new intensity, let me call it intensity number 2. And so I'll call this intensity number 1. And the only thing I've changed here, determine the intensity of the result if the frequency has increased to 2.5. So this right here becomes 2.5 of the original frequency. And so maybe I should call this original frequency. Because when you write all this out, putting the original stuff together, then you would just have this multiplication factor of 2.5 squared right next to it. And so you could take all those factors and call it 0.6, since that was the original intensity, and then has gone up by 2.5 squared. So 2.5 squared is 6 1/4. So it's 6 1/4 more than the original 0.6. And so we're at 3.75 watts per square meter. And I think that's a little easier than, again, taking an extra step back here to figure out what this is and then just putting it back in to get that number. But either way, you should get that same number. So that's A. And I think the same thing can be said about B, where it says here, calculate the intensity if the frequency is then reduced by a factor of 1/2. And the displacement amplitude is doubled. Okay, so let's call this intensity number 3. Because using this same equation, I'm now going to take the frequency and cut it in half. And I'm going to take the original amplitude, maybe I should call it 1, and double it. Okay, so the frequency's cut in half, but the amplitude's doubled. And then hopefully you'll see that if we put the original stuff together, and then this stuff squared would be 1/2 times a 2, which is together is just a 1, and a 1 squared doesn't change anything. And we're back to the original 0.6 watts per square meter. So again, that's probably the easiest way instead of actually getting all these individual numbers and then plugging them in. But that would work too. And so, ta-da, there's number 3. So yeah, I see why this is a black problem, but I also can see why it could be a little longer problem depending on what approach you take. But hopefully that helps. All right, let's go on to the third one here. Actually, you know what I'm thinking? Maybe I'll cut this video into 2 pieces. I wanted to do all 6, but I think these other ones might take a little while. Maybe not as long as this first one here, but they might take a while. And so it might be better if this was in 2 pieces. So I'll stop this and then start another video. All right, take care.